So just by show of hands, how many of you have heard of immunotherapy? You can thank the New York Times, CNN, Newsweek, and everyone else for that. So that's awesome. So the goal for today is to sort of go back to the basics and to orient you a little bit about immunotherapy. Like everything else, you can't always believe what you see on TV. And so the goal is to lay out the groundwork first on how our immune system works, which can be quite confusing. Orient you through the interaction between our immune system and cancer cells. And then I'm going to focus specifically on what we know about GIST in the immune system and highlight some clinical trials that are ongoing. So when we look back through the years, we can see that cancer care has really evolved. And you have to add about 20 years to this timeline for sarcoma because we're just behind. But surgery obviously has been around the longest. Radiation and traditional chemotherapy for GIST, of course, has had limited utility for standard treatment. But GIST really has led the way in the fourth pillar of cancer therapy, which is this idea of precision therapy. And again, as Dr. Trent mentioned, this involves using our understanding of the genetics, what's actually driving the tumor, and then using a specific therapy that can shut down a protein that does that driving of the growth of the tumor. And so immunotherapy is a little bit more recent, and this is really becoming the fifth pillar in many people's view. And in general, it's this concept that we can boost the immune system in order to attack cancer. I would argue also that in the future we're going to see a couple of new pillars. Epigenetics is really a system that regulates the genetic activity globally. There are drugs that can specifically reprogram the genetics of cancers. And then metabolism over there on the left, which involves trying to understand how cancers feed themselves and disrupt that. But I won't talk about that today. So again, this is our outline and what I'll talk about. Avoid detection by the immune system, what's important in GIST, and then some clinical trials. Okay, so to kind of start, let's look at a normal healthy immune response. So I'm sure all of you have had the flu or a nasty cold at some point, right? So what happens is that flu virus, which is somebody sneezed next to you and you picked up, it's depicted here. This word. I'll use the mouse. Okay, so here's our flu virus. So flu in particular, or any virus, has these little studded proteins on its surface that are very foreign. And those proteins, which the other fancy name for those is antigens, can be recognized by our immune system that's circulating our body and basically the patrol to look for any foreign invaders, if you will. And so there are particular cells called macrophages or dendritic cells globally that are called antigen-presenting cells. And so these are the security officers that find this rogue protein-studded flu virus floating around. They eat it, they digest it, and then they present those particular proteins on the surface of themselves. So they're basically tattling to our immune system, the more sophisticated parts of our immune system, which include T cells. So T cells have the ability to recognize the foreign invaders, the protein specifically. They send a signal to their friends. They generate a whole army of other active T cells who are specific for the flu. And so that army is what mounts the response, can really get rid of and digest all of those flu particles and get rid of the viral infection that you're going through. So these have to be activated and they have to have the signal to attack. And in large part, cytokines, which are proteins in the body that make us feel horrible when we have a viral infection, help to stimulate things along the way towards that active, inflammatory, attacking state. And so at some point, this is done, right? So all your flu viruses are taken out, and it's time for you to feel better, because if this went on forever, none of us would be happy. And so the key with the immune system is that it has to have a way to shut itself down. Okay, there has to be a yin and a yang. We want our immune system to be active and inflammatory when it's necessary, get the job done, and then shut off. So this is a busy slide, but I want to just highlight a couple of things. The key is that there are particular cells or particular stages of our immune cells that are more inflammatory, more activated. And on the other hand, there's phases of our T cells that are more suppressive, that act to shut down the immune response. And so one of the cells that I'll talk about quite a bit today is something called a T regulatory cell, or Tregs. There are two different kinds of macrophages. Remember, macrophages are the antigen-presenting cells, the ones that can eat things. The M1 macrophages tend to be more active. The M2s tend to be suppressive, so everything's in balance. Cytokines are the same way. There's activating cytokines that make you feel like you have the flu, and then there's the cytokines that finally ease up on you and tell the immune system to shut down. And finally, there are a lot of interactions that happen. So just like Dr. Trent talked about KIT as a protein antenna on the surface of GIST cells, that job is to carry signals from growth factors that are in the circulation and carry that down into the cell. And so similarly, there are receptors on the surface of immune cells that stimulate inflammation and then suppress inflammation. And so we'll talk a lot about something called checkpoint proteins, which are shut-off mechanisms, okay? These are proteins that, when activated, shut down the immune response. So let's take a step back. All of you ask me when you come into my clinic, what can I do to make my immune system healthier? Because we know and we inherently sense that if our immune system is active, we should be less likely to get cancer. Makes sense, but at the same time, this was actually a concept that was identified way back in the late 1880s by a guy named Dr. William Coley. So what happened was he had a patient with a sarcoma. He did a surgery and removed the sarcoma, and the guy got a horrible strep infection, so terrible infection. And I think he had metastatic sites or some other sarcoma there. And after that strep infection, the sarcoma magically melted away. And so he's really credited to being the first person to say, if people have a robust immune response to an infection, maybe we can cure cancer. And so what he started doing was going around and giving his patients bacteria in their bloodstream to try to cure their cancers. And that obviously didn't go well for most patients. And so what's happened is over the years, people have sort of dreamed about coming up with a way to figure out how to boost the immune system to fight cancer, but it's really sort of been an up and down process over the years. So this is another complex diagram, but I'll walk you through it. So in 2011, these researchers in this very famous paper kind of formalized Dr. Coley's idea in something called the immunoediting hypothesis. And so basically what this means is that, let's say you have normal cells that have a mistake from whatever exposure, they're exposed to cigarette smoke, or in the case of GIST, something happens that we still don't understand to boost that mutation or to cause that mutation in the KIT gene. And so what happens is that initially, any mutation in a cancer cell often will produce an abnormal protein. And so those abnormal proteins also can be on the surface of a cancer cell or a newly transformed cell. And there are immune cells in our body whose job it is to recognize our own invaders, our domestic terrorists, if you will, as opposed to the outside flu vaccine or viruses. And so our immune system is always surveilling this as well. And so ideally, it might recognize an early cancer cell, maybe the first or the second cancer cell that's transformed, and be able to eliminate it through a very similar pathway. And you need very strong inflammation in order to do this. So you need activated immune cells, the right cytokines to pull this off. So what happens if in this collection of cancer cells, there's some tumor cells that the immune system can't recognize? Maybe they don't have the right proteins, or for whatever reason, they're just not picked up as well. They're hiding somewhere that the immune system can't get. What happens is those cells, the resistant cells, can hang around, and over time, through survival of the fittest or selection, the cancer cells become more and more shifted towards those resistant types. Our cancer cells are also very smart. They can co-opt or figure out ways, just like our normal cells, to avoid the immune system recognizing them as being bad. And I'm going to go through this in more detail. But over time, with all of these adaptive mechanisms, they become even better able to avoid immune detection. And the immune system ultimately shuts down, just like it does in a flu illness. It finally gets to the point where it gets tired and it starts to become more suppressive. And so this is what happens when the tumor is able to continue to grow and escape the immune system. So in order for us to design treatments to boost the immune system, there's a couple of things that need to happen. So again, as I mentioned, we need to have the right proteins or antigens expressed by our cancer cells that can be actually recognized by our immune system. We need to be able to actually recognize those proteins as being foreign in order to have a good response. And so cancer cells can actually either lose their antigens, so they don't express anything, and this is very common in sarcoma, or they can actually produce chemicals that send the immune system more towards the suppressive side. Think of it like a teeter-totter. They can also produce those same suppressive cytokines, and it keeps the immune cells from being able to get into the meat of the tumor, which is where they need to be face-to-face in order to kill it. And then finally, tumor cells can actually express those same shutoff proteins, the checkpoint proteins, that our normal cells use in order to avoid being detected. And so the goal of immunotherapy is to try to combat each of these different steps in the process. So these are some of the ways that the cancer cells avoid detection, and we try to block those ways that the tumor uses. And so many people have described this as driving a car. So if you think about it, you need the right keys to the ignition. So that's the tumor-specific antigens. So if the tumor doesn't have proteins that can be recognized, people have tried to give vaccines, okay? So this makes sense, just like the flu. We have a protocol at Sylvester where when patients go to have surgery for a sarcoma, we actually take their tumor and we freeze it down and digest it in the lab, creating a slurry, if you will, of that patient's individual tumor. So again, on our vaccine trial, patients will use a special cream. It's called imiquimod, and that actually draws the immune cells, those antigen-presenting cells, to the site where we're giving you your injection. So we try to help promote a very active recognition and presenting by the macrophages and the dendritic cells. The next step after all of that happens is that we need our T cells, the parent cells, to generate an army. They need to proliferate, they need to be specific for whatever protein we're trying to send them after. And so one way that people are trying to get around those initial steps, which is recognizing the protein and presenting it, is to just generate the T cells. And I'll talk about this towards the end of the talk, but the concept is that you can actually engineer your own T cells to be specific for a target. And then we can give those engineered T cells back to patients, sort of bypassing those initial steps in the antigen recognition process. Finally, there are many therapies that can improve the migration, getting T cells into tumors, the roadmap, if you will, and many drugs that include drugs like sunitinib, regorafenib, actually also have effects on a protein called vascular growth factor, which is important for migration into tumors. Finally, we need to flip the T cell balance so that they're activated and not the suppressive types. And so there are many drugs. This is where the bulk of the research that you're seeing on TV is coming from. There's over 50 different receptors. Some that if you use a drug to stimulate them, they will make the immune cells more active. And then others that are suppressive, so if you block it, you will block suppression. So there's a lot of double negatives going on here, but think of it like the don't eat me signal. So the tumor has a checkpoint protein on its surface, your immune cell comes along, and when it interacts, the checkpoint protein effectively serves to shut off the immune response. Checkpoint inhibitor drugs block that interaction, okay? Leading to activation. Okay, so now I'm going to shift gears a little bit and talk about what we know about the immune system in GIST. So what we know is that GIST actually do have pretty significant immune cells already in the vicinity. So this is reassuring because that means that at least our immune cells, in many cases, are in the right location. The idea is that then potentially we could make them more active and more effective if we've already accomplished those first steps in the process. And so this is work that was reviewed by our pathology group and also from Dr. Van Dongen and all. And so what they showed is that inside of GIST tumors, the general environment, while there's a lot of immune cells there, they tend to be suppressive. So they have a lot of these M2 macrophages, so not very smart antigen-presenting cells. They have T regulatory cells. And then also, what they show though is that there are CD8 T cells. So CD8 are the ones that can actually go and attack cancer. And so this is a picture, a dot plot here, showing that in many patients there are actually very high numbers of T cells, and also that we see our regulatory T cells around as well. What's interesting is that those suppressive macrophages tend to be higher in metastatic tumors as opposed to early localized tumors, so this gives us some important information as well. These are just some pictures showing the immune cells in the tumor tissue. This is another study that was very interesting, I thought, and it shows that these are markers for different immune cells, and there tend to be higher numbers of immune cells in metastatic tumors, in higher risk tumor just that actually come in the intestinal tract, and then tumors that grow faster. So again, it suggests that our immune system's trying. Like these more aggressive tumors, the immune system is involved, it's just not quite able to make it happen. This study actually looked at whether or not having immune cells made a difference in how patients did. So these are called survival curves. And for example, this is the percentage of patients that are progression-free. So the higher the percentage, the more likely the patient is to be free of disease, or at least their disease is not progressing. And the lower that the mark goes, the less likely they are. So what this looked at is Tregs, so the T regulatory cells which suppress the immune system. Patients that had low numbers of suppressive Tregs did better than patients that had high suppressive Tregs. Patients that had high levels of regular T cells, immune cells, did better than if you didn't have any immune cells in the vicinity. And then this figure here looked at both. So these are a marker for something called natural killer cells, which I didn't talk about as much, but this is another type of natural, very strong anti-tumor immunity. And if the patients had high natural killer cells and high T cells, they did very well, whereas if they had none of those things, they did very poorly. And this is actually looked at next to our typical risk score. So I don't know, I don't think Dr. Trent talked about it, but often when you come into the clinic with a GIST, we'll tell you what your chances are of this coming back. And it's based on things like location, how fast the tumor is dividing. And that's one of the people that developed this score is called Meitner. And so what they looked at in this particular study is how strongly having immune cells paired up with typical risk assessment. And they actually found, again, that if you had lots of natural killer cells, if you had lots of T cells, and if you had low suppressive Treg cells, you were going to do better. Okay, so what can we make of this moving forward? So we know the immune cells are there. So this group actually looked at what happens with imatinib. So what's really interesting is that imatinib, as we know, is a KIT blocker. But what people have figured out is that it actually has significant effects on the immune cells as well through that mechanism. And so there's a lot of figures here, but basically the take-home point is that when you treat GIST cells with imatinib, you can increase the amount of T cells that go into the tumor. And you can kill off those nasty T regulatory cells, the suppressive cells. And so these are a variety of pictures showing the increase in T cells when you use imatinib. This is also in the picture as well. And what's even more interesting is that in tumors that are sensitive to Gleevec, you see a jump in the number of T cells, but when they become resistant, that goes back down. So this really suggested that maybe imatinib, by virtue of its effects on the immune cells, this might explain how it's working to some degree. And what they figured out is that by blocking KIT, they're actually stopping the production of an enzyme, a protein in the cell called IDO, and IDO does exactly what I've been talking about. IDO shuts down the active T cells that can fight the cancer, and then it also leads to growth of the suppressive Tregs. So again, with the double negatives, but if imatinib blocks IDO, you're going to shift the balance back towards the good inflammation and away from the suppression. And so in these experiments, what they did was they used an IDO inhibitor or imatinib, which basically does the same thing, and they could show that they could kill off Tregs with either treatment and also improve the amount of good inflammation T cells around. So what they did also is they said, okay, so imatinib is boosting our good immunity. We're getting good CD8 cells, the T cells, and we're getting rid of Tregs. What happens if we throw in one of those checkpoint inhibitors, which, as I told you, is another way to shut off the immune cells? And so these are mouse models, and when the blue line here shows just the checkpoint inhibitor, CTLA4 alone, and the red line is the combination of Gleevec. The black line is just Gleevec alone. And you can see, based on this, that this is tumor volume on this side here. There was a drop in tumor volume with the combination therapy. And so this actually led to a clinical trial that was run out of Memorial Sloan Kettering with Sandra D'Angelo, Bill Tapp, and their group. So this is a busy slide, but the take-home point is that they combined a drug called ipilimumab. I can't say that twice. Yervoy is the other name. But this is that checkpoint inhibitor, plus a drug called dasatinib, which is another type of kinase inhibitor like Gleevec. And so they enrolled patients with sarcomas and with GIST, including 20 patients with GIST tumors. It wasn't the greatest study to sort of prove this concept, only because most of the GIST patients had already failed imatinib, or their tumors grew despite imatinib. And so dasatinib, although it has some activity, might not be the standard next drug that we would go to. But even with that, there were patients here who had what we call complete responses, meaning their tumors melted away completely, or at least shrinkage in their tumors. So this is another checkpoint protein called PD-1. Now this is the famous one that's all in all the TV commercials, the drugs pembrolizumab or Keytruda, and then nivolumab or Opdivo. So you give them imatinib, and all of a sudden the tumor's like, okay, wait, I have to shut the immune system down, and so it starts jacking up another way to turn it off. When they become resistant, it goes back down again. So this is tied in very tightly. And so what people are thinking is that maybe potentially combining it with a different target, with PD-1, which is in the same family as the CTLA4 ipilimumab drug that I just showed you in the trial, might actually be better. And so this is a list of these checkpoint inhibitors, and I put Jimmy Carter here because that's what everybody says. They come to me and I want the Jimmy Carter drug, the one that made him cured. So Jimmy got pembrolizumab, but that's a whole other story. In any case, these are some of the trials that are going on now that GIST patients are actually eligible for. So there is a trial going on at MD Anderson with that same checkpoint inhibitor plus Gleevec this time instead of dasatinib. So we're hoping that this will work a little bit better. There's a study combining two checkpoints, so two checkpoint inhibitors against PD-1 and CTLA4 for patients with GIST in UCLA. There's a combination study of pembrolizumab, the checkpoint inhibitor, with a drug called cyclophosphamide that's thought to actually disrupt the macrophages. So again, trying to come at this from multiple angles is sort of the take-home point with all of this. This is a double checkpoint inhibitor study, again, that's going on at MD Anderson, and GIST are eligible for the other sarcoma arm as well. This one combines, again, a anti-macrophage drug, or really pushing the macrophages back towards the stimulatory type instead of the inhibitory type, plus pembro. And then we have our own study here that we're running that combines a drug axitinib, which blocks vascular growth factor, which I told you was important for migration of immune cells into tumor tissue, plus a checkpoint. And we enrolled just on these as well. So obviously there's a lot going on here, but the checkpoints are really like the key in media, and I think where a lot of the hope is that we'll be able to improve outcomes. So very quickly, I'm just going to show you one other thing, which is that remember back to that picture I showed you where ideally we could bypass all of this other antigen recognition and just give you the T cells. And so this is something called a CAR T cell. And so what we do here, if you're going to make a CAR, you harvest the patient's own T cells. So basically, just like you're donating blood, they are able to pull out your own T cells out of your body. And then they program them in the lab. So they basically change that specific protein receptor on your T cells to be specific for whatever target they want. It's trickier than that, but that's the gist of it, no pun intended. So, Dr. Katz and his group up in Rhode Island actually published this paper a couple of years ago because they're trying to develop one for KIT. So how cool would that be if we have a way to target KIT, because we know that GIST cells have KIT on their surface, potentially. Now, this becomes a little tricky because you have to, we have normal cells that have KIT on them as well, and so figuring out the right combination in a CAR T cell that does enough attack but doesn't hurt people is a tricky process. But if you follow the media, there are patients with leukemia and lymphomas, blood cancers, that have had amazing responses, even close to cures, with CAR T cells specific for their target. And so a lot of people are very interested in figuring this out. And so, again, there's a lot of work left to do, but in their study, when they gave the mice the KIT-specific CAR T cell, these are mice that have GIST, they did see a decrease in the tumor growth. However, again, it needs a lot more work before it's ready for patients. So the challenges, as I mentioned, GIST are sort of problematic. So a lot of patients say, why, treat me with immunotherapy. But we just heard from Dr. Trent how there's all these tyrosine kinases. I mean, Gleevec is still, you've got a 90% shot if you have a standard GIST of getting some durability. So how do you know when participating in a clinical trial is a good idea? And I think it's very tricky because we have no evidence yet, whether, apart from that trial that I showed you, about whether immune therapy, and specifically checkpoint inhibitors, are going to be a good move for GIST patients. Most clinical trials require you to stop your other treatment. So, and often you have to do something called a washout, which means you're off your sunitinib or your Stivarga for 2 to 3 weeks. We tell you never, ever, ever stop because your tumors can flare and they can grow quickly. So, and then the immune therapies also take a long time to kick in. So even when they work, it can be months before they actually kick in and start doing anything, and even in other tumors. So you really have to think smart about what trials you're going to participate in and whether it makes sense without any good data thus far to say whether this is going to be an effective strategy. So again, I'm biased because I have one, but I encourage people to look for combinations where there's at least something that's likely to help you to some degree, plus the unknown, as opposed to just an immune drug by itself for GIST patients. Okay, and so I realize that was a lot and very confusing, and confuses doctors, any non-immunologists, to shake their head when we talk about the immune system and cancer. So if there's things that you missed, we do have copies of the article I wrote last month in the GIST and Sarcoma Journal through Raft group that sort of summarizes most of what I said, hopefully more understandable than me, but if you have questions, I'm happy to take them this time. Thanks.